This is the last section of Chapter 9, Reducible Differential Equations. And there isn't any new content in this section. It's just using the knowledge that we know about differential equations and how we can use substitutions to make the differential equations easier to solve, and then we substitute back at the end. It's just using that knowledge to apply to modeling type questions. So in this modeling type question here, it says that a particle is moving along the x-axis and its displacement is x meters, is modeled by this differential equation that's been given here, and we've got limits on the value of t. So it's only valid when t is between 0 and 1.5, where t is the time in seconds, and we've been given this substitution here to use to show that we can basically use that substitution to get from the original differential equation to this one here. So before we dive in, let's look at what has been substituted. Well, this contains x, this doesn't contain x, it contains u. So in part A, we basically want to eliminate x and replace it with u's. So the substitution I've been given is u equals xt. So I basically want expressions in terms of x so that I can eliminate them. So if I rearrange this, I'll get x equals u over t, which I could also write as u t to the minus 1. Now we also need to eliminate this term here, dx dt. So we are going to differentiate this to find dx dt. So that means we are going to be differentiating this with respect to t. Now we're going to be differentiating a product. We'll call this part of the product u and this part of the product v. So we're using the product rule. So if u equals u, then du dt, so remember we're differentiating this with respect to t, will become, well, you differentiate the u as if it was a t, so it become 1, but then we write du dt to show that we've differentiated that u with respect to t. Then the v part, well, v is t to the minus 1, so dv dt, or v dash, is going to be negative t to the minus 2. So now I'm ready to put those in. So u, which is just u, times by v dash, or dv dt, that's going to be minus t to the minus 2. And the other part of the product is going to be v times by u dash, or du dt, so that will be t to the minus 1, or 1 over t, times by 1 du dt, or just du dt. So I could leave it like that, or maybe I could express it like this, that dx dt is minus u over, let's write it like this, t squared, plus 1 over t du dt. So I've got my substitutions. So dx dt here I can replace with this, and everywhere I see x here and here, I'll replace them with u over t, or ut to the minus 1. So let's do that. Let's go to the substitution now. So we've got t times by dx dt. Dx dt is this, so minus u over t squared plus 1 over t du dt, plus x, so we're replacing x with u over t, equals 2t cubed, and x squared we're replacing with u over t all squared, so that will be u squared over t squared. So if we simplify this, we will get minus u over t, so I'm expanding the brackets, plus du dt, the 1 over t and the t cancel out, plus u over t equals, now these t's will cancel down, just leaving t to the power 1, or just t, leaving 2t u squared. Now if I have a look on the left hand side, I've got minus u over t plus u over t, so those cancel out, and that leaves me with the expression that they want, which is du dt equals 2u squared t, if I just swap the u term and the t term over. So we've proved that as required. Okay, part B of this question says, hence show that the general solution to the differential equation is this. So we are going to solve this and then substitute back, because this is going to be easier to solve, to integrate, than the original question that we started with. Now I'm going to solve it by using separation of variables. So if I rearrange it, well, let's actually just write it down. So du dt equals 2u squared t. Let's put all the u terms on one side, the t on the other. So I will have 1 over u squared, I'll leave the 2 where it is, du equals 2t dt. So I will now integrate both sides now that I've separated the variables. So integrating 1 over u squared, which is the same as integrating u to the minus 2, will become minus u to the minus 1, or we could say minus 1 over u, equals, and then 2t integrated will become t squared plus our arbitrary constant. So we could write this as minus 1 over u equals t squared plus c. Now we need to substitute back, and u is equal to x t. So it might be helpful actually, before we substitute in, to do the reciprocal of this, of both sides. So I'll have negative u equals 1 over t squared plus c. Now I'm going to move the minus sign over just to make the substitution a bit easier, and actually incorporate the minus sign in this denominator here. So rather than right at the front, and then what I'll have is negative t squared minus c. And then I'm going to substitute, but also at the same time I'm going to call this constant here, negative c, I'm going to call it a. So I'm just going to write here, let a equal negative c. So I'm going to use a, because if I have a look, I've got a as the arbitrary constant there. So u now I replace with xt equals 1 over, now I wanted to make it look like this. Now if I swap these around, like instead of writing negative t squared plus a, I'll write a minus negative t squared. Then last thing I need to do is just to divide both sides by t, and I'll get 1 over t times by a minus t squared. So we've got the result that they wanted as required. And then lastly, in part C, it says, given that x equals 1 when t equals 0.5, find a displacement after 1.2 seconds. Well, the first thing, x equals 1 and t equals 0.25, these are our initial or boundary conditions, and we're going to use those to find the arbitrary constant. Once we've found the value of the arbitrary constant a, we can then substitute in t for 1.2, and that will give us the value of x, the displacement. Okay, so let's just write down at x equals 0 and t equals 0.5. we will have 1 equals 1 over 0.5 times by a, our arbitrary constant, minus 0.5 squared. So we're just going to work that out to work out what, calculate what a is. So that's 0.5 a, I'm going to multiply the brackets, minus 0.5 cubed equals 1. So all I've done is just rearranged it, multiplied out the bracket. So 0.a minus 0.5 cubed, that must equal 1 because this whole fraction equals 1. And from there, I will have a equals 1 plus 0.5 cubed divided by 0.5. So we'll work that out and see what we get for a. And that gives a is 9 over 4, which is 2.25. So we've got our arbitrary constant. So we can now write our particular solution, which we can use to find the value of x with a given value of t. So our particular solution now is x equals 1 over t times by, let's use the 9 over 4 minus t squared, like that. So now at t equals 1.2, all we need to do is to substitute in 1.2 into this to work out our value of x. So 1.2, 9 over 4 minus 1.2 squared, and we'll plug that in our calculator and see what we get for x. So that gives us an exact answer of 250 over 243. Let's have a look to see what that is as decimals, and 3 significant figures. So we'll get 1.0 and then it's 288. So 1.03, and the units are for x meters. So there we go. We have now done a modelling question with our differential equation. So you should now be able to do exercise 9C on pages 186 to 187. So there isn't really a recap to do. Just use the techniques which you've learned in the previous section for solving these differential equations, and just apply those methods to solving these modelling type questions. So maybe I'll just write use methods from sections 9.1 and 9.2.